In this segment, we're going to discuss a type of reaction that will allow us to add H and OH across a carbon-carbon double bond in a way that goes opposite Markovnikov's rule. So as we get started here, let's do a quick review of the ways that we've learned to convert alkenes into alcohols. So we'll look through a review here of our ways to convert alkenes into alcohols, beginning with the first way we talked about, which was to use an acid catalyst such as sulfuric acid and water. This reaction featured following Mark's rule, where we added our H to the less substituted carbon, that is the one on the terminal there, which is a primary carbon, and our OH to the more substituted carbon here. But in this case, remember that with this addition reaction, since we form a carbocation intermediate, the actual addition of the OH means that we have a carbocation rearrangement during the middle of the mechanism, so that we end up actually putting the OH group here after that carbocation rearrangement takes place. This particular reaction is generally not stereoselective, regardless of whether you're dealing with a cyclic alkene starting material or an acyclic alkene starting material. The reason it's not stereoselective is because there's a carbocation intermediate involved that is not stabilized by resonance or any special three-membered ring structure or anything like that. So this is our acid-catalyzed hydration. And the fact that Markovnikov's rule is followed and that there's carbocation rearrangements that can take place could be considered as a benefit or a pitfall, depending on what the desired product is. But in this situation, it really is what it is. When you add acid and water to this particular alkene that we see here at the top, the final product you're going to get is the one shown on the right as the major product. If instead your goal is to start with that same alkene, but instead put the hydroxy group at carbon number 2 of the chain, your best bet is to do oxymercuration reduction, because oxymercuration reduction, which is the reaction where we first start with our oxymercuration reagent with water and followed by reduction with sodium borohydride, will give us obedience of Markovnikov's rule, but it will enable us to avoid doing any carbocation rearrangements. And the reason it avoids a carbocation rearrangement is because, as we saw in the last segment, the intermediate is stabilized by resonance by making a three-membered ring that involves the mercury as one of the atoms of the three-membered ring to circumvent the possibility of a carbocation rearrangement. With oxymercuration reduction in particular, when we're dealing with molecules that have a ring to start with, meaning cycloalkenes, we'll generally notice that anti-addition is what we will observe. So the H and the OH will add trans to one another. So our third type of addition reaction that will give us alcohol products, and that's going to be our focus of this segment, is hydroboration oxidation. In hydroboration oxidation, what we do is we will take an alkene and we will mix it with borane, BH3. Borane can also, by the way, be shown as B2H6, the dimer version of this. So B2H6 is another way you'll commonly see this written. After that reaction is completely finished, we would then add to the reaction sodium hydroxide as well as peroxide to give the oxidations of this reaction mixture. Oxidation is done via the peroxide there. So this particular reaction, hydroboration oxidation, is super useful because it is the only option we have on the table right now for going against Markovnikov's rule to add a hydroxy group and hydrogen across the carbon-carbon double bond. You'll notice here in the product that we report that our OH group goes on the less substituted carbon, and the hydrogen that's been brought in ends up going on the more substituted carbon. And so that's totally opposite the regioselectivity of the other two reaction types that we've talked about. So this is going to be advantageous in terms of getting to the desired constitutional isomer that we want as the major product, if our major product corresponds to having the OH on the less substituted carbon. The other thing that we will need to keep in mind about this reaction is that we won't ever have carbocation rearrangements, so we don't need to worry about that. In other words, straight away we can add H and OH across our carbon-carbon double bond, not worrying about the skeleton of the molecule rearranging. That helps us to straightforwardly predict the product of these reactions. And This reaction, if we're dealing with a ring in particular, is going to give a syn addition of H and OH, meaning the H and OH will add to the same face of the molecule. So let's do a couple example problems of this hydroboration oxidation. The mechanism for this reaction is beyond the scope of what we'll be covering in this particular course. If you're interested in what the mechanism of this looks like, there's certainly resources out there, both in the textbook and internet, for the hydroboration oxidation mechanism, but it's not something that I expect you to know for purposes of this class. You should, however, be able to take a starting material and predict what the final product would be. In other words, if you take an alkene and react it with borane, followed by peroxide and hydroxide anion, what are you going to get as the final product of that reaction? So let's do examples that illustrate what I would expect you to know about a hydroboration oxidation reaction, and that is, I expect that if we started with a particular starting material, whatever you like there, like so, and you saw that we were reacting with borane, which we can list as BH3 or B2H6, as well as peroxide, and the hydroxide anion is the portion of the sodium hydroxide that's necessary here. So I'm just going to put OH minus for the hydroxide anion. You could certainly use potassium hydroxide here. The main thing is you got to have a source of OH minus. So we ask what the major product of this reaction is, including stereochemistry. And we need to keep in mind those key facts that we know about hydroboration oxidation, that it goes opposite Mark's rule, and that there will be no carbocation variance. So going opposite Mark's rule means that we need to add what here? H or OH. This is the less substituted carbon, and going against Mark's rule means that the OH goes on the less substituted carbon, the H goes on the more substituted carbon. So I would just put H adds here, OH adds here, and then let's go ahead and draw out the product that would result from this, or products that would result from this. So we're doing showing our regioselectivity here. So go ahead and plug in our H, which we've added right there, OH, which we've added right here, to give our addition product. And so in this particular situation, you'll notice that we actually have created an achiral product, because if we take a look at our carbon atom right here on the terminal end, that's not a chiral center, not a chiral center, not a chiral center because it has two identical isopropyl groups bonded to it, not a chiral center, and so on. So therefore, we are good to go with this molecule as is. We don't need to draw any wedges or dashes for it since it's not chiral. It doesn't matter. It's certainly, the carbon shape is still tetrahedral, so you can draw wedges or dashes, but you're creating extra work for yourself if you do. So let's take a look then at another example problem here, and we're going to go ahead and bring in an example that involves alkene group that is part of a ring. So we'll go ahead and use the same reagents again. So I'm just going to put my ellipses here to indicate we're using the same reagents as up top. And we keep in mind here that we are going opposite Mark's rule, and that if we're dealing with a ring system, that we're going to have syn addition of H and OH. So here, keeping in mind that our H and OH are going to be syn to one another, we actually don't have to really think about regioselectivity here because both of our carbons are equally substituted. So it doesn't matter which one gets OH and which one gets H. We're going to be in the same situation one way or the other. But keep in mind that those groups are going to be syn to one another. Syn, you could think of it like cis. That means that the OH and the H both have to be wedges or both have to be dashes in order for those to be syn to one another. So I show both of them as dashes, and then I'll show them both as wedges. And this will illustrate that this reaction is indeed stereoselective because of the fact that we aren't making the trans products here. We're only making the cis products. So there we go with our enantiomer of that structure reaction product that we showed up top here. So these are going to be our two major expected products of the reaction mixture corresponding to our syn addition or cis addition of H and OH across the carbon-carbon double bond. Let's do one additional example to finish this up. And again, No need to write out mechanisms for these. You'll just be plugging in the H and OH into the proper location of the final product for these example problem types. So we'll go ahead and show this as our starting structure. Again, use the same reagents of borane followed by the peroxide and hydroxide anion. I'm going to draw out the skeleton, and it's safe to go ahead and draw the skeleton straight away here for the molecule because we expect no carbocation rearrangements, so all the atoms that we start off with will still be in the same place at the end. We're just going to be replacing that carbon-carbon double bond with H and OH going opposite Mark's rule. So going opposite Mark's rule means that our OH that we're bringing in is going to be added to the less substituted carbon, so that's going to be that carbon on the end is going to pick up OH, and the carbon adjacent to it right here is going to pick up H. So now, at this point, does this molecule have any newly created chiral centers? The answer is that yes, it does. Carbon number 2 of the chain, that's this carbon right here, is a chiral center. Since this molecule is not cyclic, we expect that chiral center to be a mixture of the R and the S enantiomers. So let's go ahead and show that, and I'll show it in a way that's most realistic of a line angle formula, where we're not showing the hydrogen explicitly in most line angle formulas, because that's implied that it has to be there. So wedge to our methyl group, or alternatively, as our other stereoisomer product, we can show a dash to that methyl group instead. So this gives us our 2 major expected products of the reaction, including stereochemistry. So if you were given a problem, which is a very realistic situation, of being asked to provide the major organic product of a reaction, such as hydroboration oxidation, this is what you would need to show, what is here in the right-hand column, the final structure. You do not have to show a mechanism to indicate how you got to that product. You just need to show the final organic product. So this is what we mean when we say predict the major organic product of a reaction, including stereochemistry, is showing structures like we're showing here at the far right. And since we did not go over the mechanism for hydroboration oxidation in this segment, you do not need to be familiar with how to show the electron pushing arrows to go from the starting material to the product. You just instead need to train yourself to recognize this combination of reagents that we see here of borane followed by peroxide and hydroxide anion will give addition that is opposite Mark's rule and has no carbocation rearrangement. So that about covers it for our hydroboration oxidation. That is our 3rd way that we've learned to make alcohols out of alkenes doing these addition reactions.